section 15.3, we're going to be talking about Hamilton paths and Hamilton circuits. Notice I said Hamilton paths, Hamilton circuits. These are different from Euler paths, Euler circuits. If you recall, when you have an Euler path, Euler circuit, you have to hit every edge. When talking about Hamilton, this is going to be something different. So, a path that passes through each vertex of a graph exactly once is called a Hamilton path. If a Hamilton path begins and ends at the same vertex, passes through all the other vertices exactly once, it is called a Hamilton circuit. Notice the difference between an Euler path and a Hamilton path. Euler is edge, Hamilton is vertex. Find a Hamilton path for the graph. Find a Hamilton circuit for the graph. Remember, we have to hit every vertex. So maybe one example would be A to B, B to C, C to D, and D to E. And I've hit every vertex, so that would be an example of a Hamilton path. Hamilton circuit, if I extend that path to go back to A, now I have a Hamilton circuit. Complete graph, this is a definition. A complete graph is a graph that has an edge between each pair of vertices. If you look at the graph on the left, notice there is an edge from A to B, A to E, but there is not an edge going from A to C, for example. So this is not a complete graph. The number of Hamilton circuits, if we were to count up the number of Hamilton circuits, as long as we have a complete graph with n vertices, then the number is n minus 1 factorial. So if I've got 7 vertices, the number of Hamilton circuits would be 6 factorial. In the graph, there are edges between each pair of vertices. The graph is complete, and it has a Hamilton circuit. One of these circuits is A, B, C, D, A. So A, B, C, D, A. Any circuits that pass through the same vertices in the same order will be considered to be the same. So if you look at these examples of circuits, Hamilton circuits, notice this one starts at A and ends at A, this one starts at B and ends at B, but they're considered the same because I go from A to B to C to D to A to B to C to D to A. Notice these vertices are going in the same order. It's just whichever one I start with changes. So as long as you're going in the same order, they are considered the same circuit. One way to avoid duplication is always assume that we're going to start at A. There are 6 different unique Hamilton circuits for the graph. There were 1, 2, 3, 4 vertices. 4 minus 1 is 3. Factorial is 6. So these are the 6 distinct Hamilton circuits. And remember, each one can be written in a different way depending on which vertex we start with, but for simplicity's sake, we're always going to start with A. If you have a complete graph and the edges have numbers attached, this is called a weighted graph. The numbers shown along the edges, those are called the weights. This is an example of a weighted graph. Notice I look at the edge between A and B. It has a number, 190. Usually, weighted graphs are used to represent cost or mileage. So in this particular weighted graph, it indicates the cost of the trip. So it would cost $190 to go from vertex A to vertex B, or usually city A to city B. $126 to go from B to C, etc. This says use the weighted graph to find the cost of the trip for the Hamilton circuit. So I want to go from A to B. A to B, that's $190. Then I want to go from B to D, so that's this edge, which is $155. Then I want to go from D to C, is $179. And then I want to go from C back to A. So that's it. This edge right here is $124. And you would add this up, and that would tell you the cost of the trip for this Hamilton circuit. Cost $648. The traveling salesperson problem. The traveling salesperson problem is the problem of finding a Hamilton circuit in a complete weighted graph for which the sum of the weights of the edges is a minimum. If I'm going to be sending salesmen out to different cities, I want to pay the least amount of airfare. So we're trying to find the minimum cost for the Hamilton circuit. This Hamilton circuit is called the optimal Hamilton circuit or the optimal solution. One method for finding this is called the brute force method. So with the brute force method, these are the steps you're going to take. So you're going to draw a complete weighted graph, make a list of all the possible Hamilton circuits. So we need all possible Hamilton circuits. Determine the sum of the weights of the edges for each of these Hamilton circuits. In other words, add up the weights for the circuits. And the Hamilton circuit with the minimum sum is the optimal solution. So we have the previous weighted graph, and we want to find the optimal solution. We have 4 vertices, which means if I take 4 vertices, subtract 1, 4 minus 1 is 3 factorial. There's 6 possible Hamilton circuits. So the first Hamilton circuit we're going to look at is A, B, C, D, A. And if we find the sum of the weights, A to B is 190, B to C is 126, C to D is 179, D to A is 157. You add those up, you get $652. The next Hamilton circuit, A, B, D, C, A. Again, we're going to add up the weights. We get 648. We do this for all 6 possible Hamilton circuits. And what we're looking for is the minimum cost. So we actually have 2 Hamilton circuits that have a minimum cost of $562. That's the smallest. And one of those is ACBDA, and the other one is ADBCA. So this actually has 2 optimal solutions. They are different Hamilton circuits. The cost is the same regardless of the direction flown. So A to C, and if I go backwards, I go A to C, then to B, then to D, and then to A. So it's like one's going backwards. But they are actually two distinct Hamilton circuits. Another method for finding the optimal solution is called the nearest neighbor method. First thing you want to do is draw a complete weighted graph. Figure out the starting point. From the starting point, choose an edge with the smallest weight until you get to the second vertex. From the second vertex, choose the edge with the smallest weight that does not go back to a vertex you already visited. Continue in the same manner until you've hit every vertex, and then go back to the first vertex, which was your starting point. Sales director lives in city A, is required to fly to regional offices in cities B, C, D, and E. The weighted graph gives the one-way airfares. Use the nearest neighbor method to find an approximate solution. So, we're starting at A, and we have our choice. We can either go to B, to C, to D, or to E. Nearest neighbor method says find the cheapest flight from City A. And the cheapest flight is $114, which will take us to City C. From City C, we have to find the cheapest flight. But remember, we don't want to go back to City A until we're all done. So our choices now are 116 to B, 116 to B, 114 to A, but we've already been to A, so we're not going to go back, 115 to E, or 169 to D. Since the cheapest is 115, we're going to go to City E. So far we've gone A to C, C to E. From E, we can go to A, but we don't want to do that because we've already been there. We could go to B, or we could go to D. D is cheaper, so we're going to choose that flight. And let me clear this off a little bit so it's a little clearer. So far, A to C, to E, to D. Now at D, we've got two choices. We can either go to B or we can go to A. And since we haven't visited B and we have visited A, we're going to go to B. We would go this way even if it was more expensive than going back to A. And now that we've hit every vertex, we're going to go back to the original city. If you add the cost, it's $748. Homework is 2 through 34 even. I also want you to do problem number 40.